As we reflect on the origin of the universe, the question arises: what existed before the Big Bang? If there was no before, then what caused the monumental explosion in the first place? For centuries, the answer seemed simple. A timeless God initiated everything. Even Isaac Newton believed that God created the universe around 6,000 years ago. However, many scientists, including a young Albert Einstein, once thought the universe was eternal and unchanging. Stars could form and die, planets could collide, and civilizations could rise and fall. But on a cosmic scale, the universe appeared largely constant over time. It wasn't until the 1930s that compelling evidence for the universe's expansion emerged. And in the 1960s, we discovered proof of its origin in the Big Bang. This groundbreaking realization in science rivaled even the heliocentric model of our solar system in its magnitude. Yet, with this discovery, two perplexing questions arose. What happened before the Big Bang? What was space like before it began to expand? And, if the universe had a beginning, does it also have an end? British physicist Brian Cox embarked on a journey to answer these questions. In a recent world-changing revelation, Cox boldly asserted that the universe existed before the Big Bang, shaking our understanding of the universe's origins. According to Cox, we used to think the universe began as an extremely hot, dense state at the dawn of humanity, an event we referred to as the Big Bang. But now, we strongly suspect the universe existed before that moment, suggesting that it is possible to talk about a time before the Big Bang. As a physicist and professor of particle physics, Brian Cox has made science accessible to the public in the 21st century, contributing to ongoing conversations and discussions. Never one to shy away from difficult questions, Cox recently addressed the story of the Big Bang. The concept of the Big Bang first emerged in the 1920s and 1930s, when astronomers observed distant galaxies moving away from us. The further away these galaxies were, the faster they seemed to be receding. This observation, consistent with Einstein's theory of general relativity, suggested that the universe was expanding. This was an incredible discovery. Today, as galaxies continue to move apart over time, it indicates that they were once much closer together in the distant past. An expanding universe doesn't just mean that objects are moving farther apart. It also means that light from distant sources shifts in wavelength as the universe ages. This process, called redshift, also implies that the universe cools as it expands. If we trace this expansion backward in time, we reach a point where everything was so hot that atoms couldn't form. If this model were accurate, we should detect a faint glow of radiation today, cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson was a groundbreaking confirmation of the Big Bang theory. From there, we can extrapolate backward further into a time when the universe was hotter and denser, until we reach an era where temperatures were so extreme that atomic nuclei couldn't form. At this point, radiation was so intense that protons and neutrons would disintegrate. This led to an era where pairs of particles and antiparticles spontaneously formed and annihilated, and eventually, the universe became a hot, dense soup of particles. This paints a very different picture of the universe's origins from the singular Big Bang event we once imagined. Now, the real question arises: what does all this mean for the actual beginning of the universe? It's possible that the Big Bang as we know it happened, but it may not mark the ultimate beginning of everything. Rather, the early universe went through a phase where all the energy that would later become matter and radiation was contained in the fabric of space itself. This period, known as cosmic inflation, ended with the hot Big Bang we recognize today. However, whether something existed before inflation or whether inflation itself was a timeless process remains an open question. One thing is clear: the Big Bang is not the beginning of the universe. If the Big Bang wasn't the start, what existed before it? The short answer is that we don't know, but the long answer is that it could have been anything, each possibility mind-bending in its own way. It's conceivable that before the Big Bang, the universe was an infinitely hot, dense material enduring in a steady state until something triggered the Big Bang. This pre-Big Bang universe may have been governed by quantum mechanics, the physics of extremely small scales. The Big Bang would have marked the point when traditional physics took over, dictating the evolution of the universe. For physicist Stephen Hawking, this moment of transition was crucial. He proposed the no-boundary condition, which suggests that the universe had no boundaries, no clear start or end points, just as the Earth is finite but lacks an edge. Alternatively, there could have been something else before the Big Bang, something worth pondering. In his documentary series Universe, Brian Cox suggested that before the Big Bang, there was no universe at all. Instead, only space-time existed, filled with an almost still sea of energy that gently rippled. This energy, Cox explained, should be imagined as a vast ocean of energy, setting the stage for the rapid expansion that followed. This expansion, known as inflation, would eventually transform the energy into matter. The universe began with a massive explosion, which left its mark in the form of slight variations in the density of hydrogen and helium gas that formed shortly after. The denser areas of this gas collapsed, eventually forming the first stars and galaxies. About 9 billion years later, our Sun was born, surrounded by 8 planets, including Earth. Nearly 13.8 billion years after it all began, humanity emerged, stepping into the light of understanding. Brian Cox isn't the only one to suggest a remarkable theory about the universe's origins. Recent theoretical physics research has uncovered a potential window into the early universe, hinting that what we perceive as the Big Bang could be part of a much larger, ongoing cycle, possibly one that has been occurring for eons and perhaps will continue forever. The physics we currently use to understand the early universe, an intricate blend of general relativity and high-energy particle physics, gets us only so far. As we push deeper into the first moments of the universe, the equations become increasingly complex, eventually breaking down completely. The crucial sign that there's still more to explore lies in the appearance of a singularity or a point of infinite density at the start of the Big Bang. This suggests that at one time, the entire universe was compressed into an infinitely small and dense point, a concept that seems nonsensical. This indicates that we need new physics to solve this puzzle, as our current theories are insufficient. We need something capable of uniting gravity with the other forces at ultra-high energies, and this is exactly what string theory proposes. String theory suggests a model of physics capable of handling both gravity and other forces at ultra-high energies. One of its earliest ideas is the erotic universe, from the Greek word for conflation or fire. In this view, the Big Bang wasn't the beginning. Rather, it was just a part of a larger process. This idea evolved into a theory known as cyclic cosmology, which suggests that the universe undergoes a cycle of big bangs and big crunches, potentially repeating endlessly. Although the concept of a cyclic universe is ancient, string theory provided it with a solid mathematical foundation. However, early versions of the cyclic model struggled to match observational data, particularly with respect to the cosmic microwave background, the faint light left over from when the universe was just 380,000 years old. We cannot directly observe beyond this light, and any theoretical modifications to the early universe physics affect this background, making the cyclic universe appear both promising and flawed. Nevertheless, recent research has revisited these challenges, suggesting that there may have been missed opportunities. These scientists study a theory known as the Big Bounce, in which the universe expands and contracts in a vast cyclical timeline. Some proponents of this theory believe it occurred only once, while others think it is an ongoing process. Though still not fully understood, supporters of the Big Bounce argue that it may offer a more comprehensive explanation than the Big Bang model, which relies on the idea of inflation, an extremely rapid expansion of the universe after the Big Bang. Inflation proposes an infinite number of universes, with ours being just one isolated bubble among many. This concept challenges the idea of a specific origin, raising questions about what might exist beyond our universe. In contrast, proponents of the Big Bounce model argue that it could provide a complete explanation without needing to invoke the idea of a multiverse. This theory suggests that before our Big Bang, there was another universe, where entropy increased towards the past, possibly even reversing the flow of time in a mirror universe. The notion of a mirror universe governed by the same fundamental laws but with reverse time and symmetry could help explain phenomena like dark matter and the expansion of the universe. These ideas challenge traditional cosmology and suggest that there is much left to explore in understanding the true nature of our universe. The idea of a CPT, charge, parity, and time mirror universe implies that it might have existed before the Big Bang or even be concurrent with our universe in a mirror-like state. In this scenario, neutrinos, a type of subatomic particle, would display unusual behavior and might even be their own antiparticles. One key prediction is that certain types of neutrinos could be massless. If this idea proves true, it would provide a significant test for this theory, especially if we find no early-stage gravitational waves, which would support the mirror universe hypothesis. As we continue to explore the origins of the universe, we are faced with profound mysteries. Our understanding has advanced significantly, but gaps remain, such as the nature of dark matter and dark energy, and the ultimate cause of the universe itself. These questions remind us of the limits of our knowledge and the humility required in the face of the unknown. Unlike popular explanations, scientific theories are grounded in evidence and data, not belief.